So this will be used to determine the noise power. KTSB, noise power of the receiver. Receiver noise power. So this are also related to this in satellite communication. We have one parameter to what I call it, to describe the performance of a receiver. We determine G over T. So this actually is receiving antenna gain over receiver noise temperature. And then the main topic will be limb budget. We also for the limb budget actually is the same. The objective is to determine the carrier to noise ratio. It's the same that you have learned in mobile communication, where you need to determine what is receive power in dB minus noise power. So by definition, the CNR actually is in linear receive power over noise power. So this in both in watt. Okay. So have you learned in principal communication, if we have in linear, there is no unit for carrier to noise ratio. So CNR, we have only in dB. We have only in dB. There is no CNR in dBm. Even though receive power and noise power can be in dB or can be in dBm. Okay, but if we use receive power and noise power in dBm, still the result for carrier to noise ratio is in dB. Okay, so that's introduction. Okay, as stated in the slide, the design of a satellite communication system is a complex process. So there are trade-off or compromise between many factors to achieve the best performance at an acceptable cost. So the second point lists down the main what I call it limiting factor related to satellite system design. The first two, cost and weight, are interrelated, because if we have more weight, then the cost will be high, including the cost for launching. Because if you have more weight of your satellite, you need to have a more powerful rocket for launching in order to bring your satellite to the orbit. But you have to make sure that, in terms of weight is required so that you can bring more fuel, and also you can bring a bigger antenna, for example, so that your antenna gain will be higher. So if you have a bigger size of equipment, So then you put more weight on your satellite. So whereas that one is required in order to achieve better performance, right? But the consequence is, or the trade-off is in terms of cost. If you have more weight, then the cost will be more. So there is a compromise, the compromise between cost and weight, and also in terms of performance. And also related to the size of the satellite. So I would say the first three are interrelated: size, weight, and cost, and performance. The last three about the frequency band, atmospheric propagation, and multiple access technique also related, interrelated. Since for satellite communication, the revenue is depend on the number of user. So if more people subscribe or use the satellite communication link, so the owner of the satellite will get more revenue. So in order to get more, to provide a service to more user, the owner should make sure that the capacity of the spectrum will be high. So this capacity is related to frequency. If we use higher frequency, then we will have more capacity. That's why, as you know, as you learn in cellular mobile telephone, so the frequency become higher and higher as we move to a new generation. So starting from second generation, about 900 megahertz. So we upgrade to third generation, 2 gigahertz. And 4G, we use up to 2.6 gigahertz. And now for 5G, we use even higher frequency, millimeter wave, about 26 and 28 gigahertz. For 5G, we have lower band, mid band, and high bands. For the high band, we use millimeter wave. So mid band up to 3.5 gigahertz. So that's when we have carrier frequency, a higher carrier frequency, then we will have more capacity. That's why maybe you have learned in optical communication. So one of the advantage of optical communication is a high bandwidth. So it's related to high capacity. But if we use a high frequency, as we know that for the satellite communication, for example, for GEO satellite, as we know that the distance is around close to 36,000 kilometers. So the 36,000 is the height. So the path length is, I would say, more than 36,000 kilometers. So at this distance, when you determine the free space path loss, so you have 32.44 plus 20 log F plus 20 log D. So if you have D 36,000, so you will have path loss is around 200 dB. So it's very high. if you use a higher frequency, then the pass loss will be higher. So the frequency and the distance will contribute to a higher free space pass loss. And even for a tropical region like Malaysia, where we have a heavy rain, for frequency above 10 gigahertz, we will have a higher rain attenuation. So that's why if you sometimes when you watch television, there is no signal. One of the factor is there is a rain. So now,
Hello, Doktor.
Yes.
Doktor, sorry ganggu. Tapi Doktor ada tunjuk apa-apa ke dekat skrin sekarang? Sebab dia macam stay je dekat slide yang sama.
Oh, ya ke? Sorry. Saya dah pergi ke second slide. So I think that's because I cannot see the slide that your view.
Maaf Doktor, sekarang baru tulisan Doktor keluar. Tadi tak nampak apa-apa yang Doktor tulis.
Okay.
Doktor bagi masa sekejap boleh nak tulis apa yang Doktor tulis kat slide?
You snap je guna handphone tu.
Okay, sekejap.
Nampak lah sekarang ni?
Lepas Doktor
Kalau
ni
saya move ni, now
Doktor try tulis apa-apa sekejap.
Content. So now I move to introduction. Can you see?
Tak, dia stay dekat content. Dia tak keluar kat introduction.
Lama tak guna ni. Kalau macam ni? Nampak? Ada?
Dia nampak tapi tulisan Doktor yang kat bawah tu dia tertutup sikit. Okay. Okay dah.
Maksudnya kalau buat slideshow dia, you tak nampak
Tadi Doktor buat slideshow ke? Slideshow tadi dia even though Doktor gerak ke slide yang lain, dia still stay kat slide yang pertama.
Sekarang ni okey tak?
Sekarang dah okey. Sekarang okey.
Nampak tulisan saya?
Tulisan nampak. Tadi tak nampak apa-apa.
Ya, saya test yang sekarang ni.
Okey, Doktor test.
Macam mana tak boleh keluar pen pula? Sekejap.
Maksudnya kalau slideshow tak boleh conteng ke Doktor?
Saya boleh conteng tapi you tak nampak lah.
Oh, faham.
So kalau macam ni okey ke? Kecil nampak?
Okey je. Cuba Doktor pergi dekat slide baru, lepas tu Doktor try conteng. Tengok dia dia keluar tak? Korang nampak tak?
So, free space pass loss.
Okay. Baru dah okey dah.
So, tak boleh slideshow lah.
Kalau slideshow, Doktor je yang nampak. Korang tak nampak.
Okay. So, saya tak payah ulang
Kalau nak ulang pun boleh juga sebab tadi tak nampak apa-apa.
Sekejap. Mana? Orang jauh baru nak join. Okay, so far in the introduction, I did mention on the limiting factors related to satellite system design. So there are compromise between cost, weight, and dimension of satellite. So if you want to have a better performance of satellite, so we need to have to put more weight on satellite. For example, we need to carry more fuel and bigger antenna and so on. But if your satellite system is more weight, then it will cost more, especially during launching. And then in terms of frequency band, atmospheric propagation, and multiple access, related to how we want to have more capacity with the limited resources in terms of frequency band or spectrum. Because all applications, telecommunication application, we need to follow ITU standard. So there are certain frequency are allocated for certain application. So for satellite, so as we have learned in first chapter, we have in Malaysia normally we use C-band, KU band, and KA band. So I did mention when we want to have more capacity, we need to use a higher frequency. But in tropical region, especially in Malaysia, when we use a high frequency above 10 gigahertz, we will have higher rain attenuation. So that's related to atmospheric propagation. So that means atmospheric effect. So it's, the main one is rain attenuation, and at higher frequency, even the gases in atmosphere, we have hydrogen, oxygen. So that's gases also contribute to atmospheric loss, especially at a frequency of 60 gigahertz. So later, I'm not sure. So at this frequency, the attenuation due to gas, for example, oxygen and hydrogen, are very high at 60 gigahertz. That's why 60 gigahertz is considered unlicensed band, same as Wi-Fi frequency 2.4 and 5 gigahertz. So as I mentioned earlier, this slide I think I can skip because this only to show the equation for free space path loss, and we have this free space path loss model to determine receive power in linear. So I think you have learned in mobile communication, right? All right. So this gives you an example of using free-space pass loss model. Some equation actually, for example, this equation is to determine the antenna gain, where we didn't use this